Okay, hi there. Welcome to this session on pre-silicon automotive software development with the Renesas R-Car virtual prototype. I'm Kevin Brand. I'm a senior staff engineer with Synopsys. I'd like to introduce Preeti Sharma, who's a co-author. She's also with Synopsys, and also Mochizuki-san, who's a senior principal engineer with Renesas Electronics Corporation. Just to quickly go through the agenda, I'll be going through a quick introduction and an overview of the R-Car SoC itself. We'll then also talk about the VDK, or the virtual prototype of the R-Car. My colleague Preeti will be going through some of the VDK development use cases, and there will be a short demo walkthrough after that. Okay, so I'd like to start by presenting a few slides from our co-author Mochizuki-san of Renesas Corporation. So I'll be presenting this on his behalf. So Renesas is a global semiconductor company delivering trusted embedded design innovation with complete semiconductor solutions. For automotive markets, Renesas offers many microcontrollers and SoCs for highly reliable vehicle control, safe and secure autonomous driving, and eco-friendly electric vehicles. The R-Car series is a Renesas SoC family for autonomous driving and ADAS, connected gateways, in-vehicle infotainment or cockpit, and instrument cluster solutions. Currently, Generation 3 products of R-Car are in mass production, and Renesas is launching the next generation R-Car for autonomous driving soon. Prior to sample release, Renesas is developing a virtual prototype of the next generation R-Car in cooperation with Synopsys. Recent problems in the automotive field are as follows. The software complexity of autonomous connected vehicles is growing drastically, while strict safety and security requirements apply. Development cycles are shrinking. To solve the problem, Renesas considers to encourage shifting left or parallelization in automotive development chains by developing a virtual prototype. The first use target of the virtual prototype is pre-silicon software development inside of Renesas, where the device and software are developed in parallel. It will result in a scheduled pull-in of the basic software package release, and another target is to enable pre-silicon software development at Renesas customers. It will encourage shift left of the software development and accelerate system development in our customers. So, let me now describe what is a VDK. Well, put simply, it's a fast software model of the digital hardware ECU or SoC. It's not a detailed model like RTL, but it's abstracted enough to run an unmodified production binary. For example, if the binary software accesses a register in a peripheral, then that must be modeled because we are executing binary code. Its purpose is about software execution, not about hardware behavior. So long as we simply model enough to convince the software that it's executing on the real hardware, then that's the level of modeling that we need to do. Typically, we are modeling at both the SoC level and also at the ECU level as well. So in terms of using virtual prototypes for software development, we see that a rather linear approach here. And that's where the SoC development is done first, and the software development is done linearly after that. So what we try and do here is we try and shift left the software development so that it overlaps with the SoC development timelines. This means that the software is in a much further advanced state when the hardware prototype appears. So this saves a lot of development time and, of course, is fully parallelized and allows for testing to also be front-loaded. With a parallel virtual prototype development, you can sort of have an incremental approach to the software development, and basically you're providing enough features in the virtual prototype to satisfy the software use cases as they're developing. So it's not the case where you need a full model to begin with, but with an incremental approach to both modeling and software based on the use cases. So Synopsys virtualizer development kits for virtual SoCs are just one part of the overall picture. Here we're showing a sort of ecosystem surrounding the model, if you like, the model being in the middle, with connected debuggers, with scripting tools, analysis tools, and also third-party connections as well. So with the VDK, or the virtual prototype, being in the middle, you can see it's surrounded in an ecosystem of tooling to allow most use cases to be executed. In terms of the use cases, what we're trying to do is support general software development. Of course, that's the main fundamental purpose, but also to do ECU system integration and testing, or virtual hardware in the loop, but also to do functional safety in terms of fault injection and coverage testing to enable iterative development. Okay, so why do we do it? Well, in many cases, it's better debug efficiency than with hardware. With the tooling itself, we have system-level visibility, we have hardware visibility, but we also have scripted control to allow us to really debug deeply into the system. This makes us much more efficient than hardware because of the level of visibility that we have in the system itself. On top of that, we have synchronized multi-core debugging. It can also be achieved with standard tools that the software user is familiar with. So this is about familiar user interfaces. So we can connect to third-party tools, third-party debuggers, and so with synchronized multi-core debugging, we can actually have a better efficiency than with hardware, because when the model is stopped at a debug point, everything stops. We also support industry standard automotive tooling. We realize that the VDK cannot exist on its own, and there's often a lot of investment in external models and external flows. So the VDK does provide a lot of capabilities and connectivity with a high-speed co-simulation interface with tools like Vector and Simulink, etc., and Synopsys Sabre. Another interesting technology, of course, is the possibility of virtual and real I/O. This is where external stimulus or externally driven communications are used for testing the software. So this can be done virtually within the tool with some scripting, but because we're running on a host machine, we can also have connectivity to that host machine. So for instance, we can use Ethernet, USB, PCI Express. We can do that sort of testing utilizing the host capabilities. So this allows, of course, a much larger array of testing and connectivity options in the virtual prototype. So with that, I would like to hand over to my colleague Preeti Sharma, who will take you through the RCAR virtual prototype and walk you through the rest of the session. Thank you.
Thank you, Kevin. Hello, everyone. My name is Preeti Sharma, and I am the R&D manager in Synopsys, and we are working on this RCAR virtual prototype. So taking the discussion forward, you can see this slide here where we are showing a snippet of this Virtualizer Studio tool. And on the left-hand side, this is more of a hardware platform composition of RCAR, where definitely it's a collaboration between Renesas, Synopsys, and ARM. So it comprises of the ARM core subsystem, including the application clusters and real-time clusters, and interrupt controller and cache core and interconnect, again from ARM. And then on top of it, we have a lot of Synopsys IPs, including the designware ones, and some of the complex custom models from Renesas. In terms of software, we are covering bare metal platform testing and, of course, the Linux bring up and the real-time operating system and drivers execution, and some end-to-end external connectivity testing for gateway protocols, and, of course, the graphics application, which is the main part of RCAR, being for the ADAS use case. Going on to the next slide, here I will very briefly talk about how the Linux boot works. So here you can see that we have a strong snippet of the UI, and it is through some powerful scripting hook we are actually enabling the Linux boot to happen. So what happens is that through the script, we actually load the bootloader, which does the basic hardware initialization, keeping all the secondary cores in low power state. So this is like a lightweight BIOS, and then it actually enables the CPU, ARM CPU subsystem to jump on the Linux kernel base address, which eventually loads the device tree. And then device tree, after loading, it actually starts configuring the devices, understanding the hardware, mounts the file system, and then finally you see the Linux boot prompt on the console in Virtualizer Studio 2. So overall, if I divide it into two boundaries, on the left hand side, this is mainly a set of hooks for consuming inputs and receiving outputs in VDK. And on the right hand side, it is like of a backend flow for Linux boot. Moving on to the next slide, this is where now I will further talk about some of the interesting use cases that we collaborated with Renesas and we covered in RCAR. So first of all, let's see overall how the RCAR iterative development has happened. So as you can see here, this has happened through different phases, where with each phase catering to some specific use cases from Renesas or for their end customers. Now, of course, with each phase, the number of models, feature sets, and software complexity is steadily kept on increasing. So one of the basic part of the use case that we covered here was Linux bring up on ARM application cluster. Here again, the objective was to enable Renesas to do some low-level driver software development for the boot support package. And the objective here was that we received some customer files, be it device tree inputs, software images, root file system, which were executed on top of Linux command. Now, overall, in this whole process, the main key learnings that was for us and Renesas was it, of course, enabled in the meaningful software evolution and evaluation. And it also helped in very early identification of both issues on the model side as well as software side. And last but not the least, as my friend Kevin already highlighted, that since there was no hardware board available, so with the virtual prototype, it was actually the real left shift that happened with Renesas. They were able to develop all their software for Linux applications using our virtual prototype. Moving on to the next slide, this is one of the other use cases for ARM RealTime Systems. So of course, in automotive, all the advanced features, they are supported through ARM RealTime cores, be it powertrain or vision ADAS or chassis. And in all these use cases, the objective here was that the Renesas software team was trying to boot some application software using the real-time code. So of course, the Linux would happen on the application code, and then there was some application on top of it on the real-time cluster. The key takeaways for us in this case was we could explore the real-time software and requirements from the customer. We also understood the importance of a separate model here that could decide that which cores to boot or to power on by default. And of course, when both cores are executing, we have to make sure that the software images exist and the memory regions don't overlap and things like that. Moving on to the next slide, this is about some of the gateway protocols that we have in RCAR, and we did some connectivity testing. So as my friend and colleague Kevin highlighted, that it is about driving the external stimulus by connecting the specific instances or models in the VDK with that of an external environment. In case of PCI, this was actually a real-world I/O kind of setup connection that we did, where we actually connected the PCI instance on the virtual prototype model to an actual PCI card slot on a Linux host machine. And all this communication happened through the HAPS 80 board, which is owned by Synopsys, and through some software on top of it that we were running. So this, of course, enabled us to do the end-to-end flow testing between these different nodes. And then on top of it, we executed some standard PCI commands that made sure that, okay, my end device is connected to my PCI device on the VDK, and the standard enumeration command like lspci is running. The other similar use case here was in context of testing the Ethernet connectivity, but this was different as compared to PCI because it was a real I/O, virtual I/O kind of testing. And I will talk more about it because it is covered as a part of demo walkthrough. So moving on to the other set of use case that we tried here is, of course, the high-end graphics and video subsystems that are main part of this ADAS use case support for RCAR advanced generation. So here we have some highly complex video signal processors coming from Renesas, and we were executing some of the software drivers and firmware on top of it. And all this was connected to a virtual LCD panel screen, which was displaying the final video or image. So this is how the overall flow looks like, where we are also using the standard video interfaces like the camera source input and display source input here. And you can see that images taken from the camera input, they pass through video processor to the display unit, and then finally to the LCD panel screens. And coming to the last but not the least use case here was the post-silicon software development. This is very interesting because as we were progressing with Renesas for their development of software with our virtual prototype, their hardware board was also being evolved. And at some point in time, the sample hardware board was ready, but it was still evolving an initial version. So what happened is that Renesas tried some of the software which they verified on the virtual prototype with this hardware board, and they could identify real issues on configurations not correct on the hardware board. One of the examples I can give here is for the incorrect ARM generic timer settings, which were actually compared with that of VP and were corrected on the hardware board. So it was very interesting to see how virtual prototypes could lead to very easy identification and fixing of problems, which is actually not very straightforward with that of hardware board. Going forward, we are targeting some more use cases, for example, more functional testing through fault injection. And of course, we continue to look forward with Renesas how their standard software development processes can actually coexist and complement our efficient integration process in the virtual prototype. Now, the last part of this slide set, I will walk you through the demo, which we have covered here. And this is mainly about testing the Ethernet application software stack. And here, overall, we are actually employing the middle layers of the Ethernet and the Ethernet drivers, which came from Renesas. And then the goal here was to test the address resolution protocol, which we call ARP packets, and just to check their request and response from this whole connection flow. In terms of test bench, we of course have this VDK where Ethernet is a part of it. It was sending the ARP packets to a virtual host machine, and it was actually receiving back the valid MAC responses. So if you move ahead, you will look here that this is how the overall picture looks like. On the left hand side, it's a VDK where we have a software image running on the CPU, which in turn is connected to Ethernet controller, generating the ARP packets, going through the file layer, and eventually it goes to a host PC, which actually have a vHub running on it, and a virtual tap network interface device connected, which actually receives the final ARP request and sends back a valid response with the valid MAC address. Now, in this whole flow, of course, the excellent source code debugging features of Virtualizer Studio were used, and we used this Wireshark tool to view all the offline PCAP logs and to check and analyze the traffic live. So this is again a snippet of the Virtualizer Studio, and the flow happens in the way that you have a design browser where you actually select your Ethernet controller model that you want to configure, and then we give a hook to load the target software image for this, and then we also have an interactive UART console which is responsive through which you can trigger the execution of your software. And on top of it, we also provide a configuration of the Ethernet controller to multiple parameters in this widget that you can see. And once the model is configured, it is time to actually enable the PCAP. And once the PCAP is enabled through this UI, then the next step is to enable some of the analysis like the function tracing in software analysis and say some of the register tracing in hardware analysis, which actually can give a very valuable insight of configurations, transmissions, and reception status on the model. And then finally, it is captured on the host machine with a Wireshark tool capturing all the logs. Then, of course, we have the overall source code debugging features in terms of analysis, where you can see there's a software on the left-hand side, and line by line, it can be debugged and analyzed for any fixes or issues. And then on the right-hand side, it is when we enable the analysis on the software side, this is how it results into a kind of function called stack tracing that you can see. And on the top, you can see the register tracing, where live you can actually see how the values in the registers are being changed and whether it is working correctly. So overall, this provides a very nice picture of how you can debug and analyze your overall software application. So, and in the end, this is about the PCAP capture. So from the Ethernet controller, you can see how the ARP packets are being sent. And then on the TAP network interface, we are receiving the response with a valid MAC address. So to summarize, what we achieved here was the customer wanted to load some Ethernet drivers, run their software. We did all that. And on top of it, we provided some seamless software stack execution and verification with the virtual interface on the host PC, and a live packet capture of network interface and monitoring through this Wireshark tool for the PCAP logs. And definitely the icing on the cake was a very complete and full-fledged support for unmodified target binaries with synchronized multi-core software debugging and a full-fledged hardware and software analysis for better insights into software execution on the hardware. So overall, I would summarize it that it was a wonderful collaboration between Renesas and Synopsys, of course, using overall the ARM set of systems that we could use. And if Renesas were using the conventional products, the productivity would have not been that good, and they claimed that it was a 4-time productivity improvement for them using our VDK solution. So it's a very nice, successful story that we collaborated with, and we continue to look forward for more. So that's all I have for today. Thank you, everyone. Thanks, Kevin. Thanks, Mochizuki-san. Have a good day. Thank you. Bye-bye.